One other preliminary before we get to what we want to do. It's the main thing today. Find the exact area underneath a curve. If you look on page 368, you will see this. And then they write a similar thing, just using summation notation, on page 372. First of all, let's make sure we understand what we mean by summation notation. You may or may not have seen this. Let me do, for example, change it for a minute. What if I had this sigma, that means sum. The Greek letter sigma means sum. As the counter I goes from 1 to 4 of I squared. First let I be 1, so that's 1 squared. Sigma means sum, so it's plus. Then let I be 2, put 2 in for I here, you have 2 squared. You always increment your counter by 1. Let I be 3. Put 3 in here, you get 3 squared. Sigma means add. Let I be 4. So this is a fancy way of writing 16 plus 9 is 25, plus 4 is 29, plus 1 is 30. This is a fancy way of writing 30. What would be the sum as k goes from 2 to 5 of k over k minus 1? Well, first you would let k be 2. 2 over 2 minus 1. You always increment your counter, which we're calling k right now. Before we called it I. It doesn't matter what you call the counter. Increment the k by 1, so I let k be 3. Put 3 in for k here. Let k be 4. I let k be 2. K be 3. Let k be 4. Let k be 5. When do I stop? Oh, I stop when k gets to this number, which is 5. So I get 2 plus 3 halves plus 4 thirds plus 5 fourths. And I could combine those into a single fraction if need be. Summation notation is just a compact way of writing a sum. So when we look on page 372 and see this, sum as I goes from 1 to n of I squared, you first let the counter I be 1 and you get 1 squared. Then you let I be 2, you get 2 squared. Then you let I be 3, you get 3 squared. You keep on going, dot, dot, dot. When do you stop? You let I be n. You stop when I is n. So this last term would be the n squared term. Okay? Do you see why we have to have this dot, dot, dot? We don't know how big n is. Now, what's this business? Y is 1 squared plus 2 squared plus 3 squared plus, keep on in that pattern, through n squared. N times n plus 1 times 2n plus 1 over 6. Is that even true? So let's check out. Let's check it out for n equal, oh, somebody give me a value of n. Somebody said 3. Okay. 1 squared plus 2 squared plus 3 squared. N is 3. I'll stop with n being 3. This formula says that's 3 times 3 plus 1 times 2 times 3 plus 1 all over 6, which is 3 times 4 times 7 over 6 which is 14. Because 3 times 4 is 12. 12 divided by 6 is 2. 2 times 7 is 14. Okay? Now, what is 1 squared plus 2 squared plus 3 squared? It's 1 plus 4 plus 9. Hey, that's 13 plus 1 or 14. These are the same. This formula is working if n is 3. And you could try it for any value of n. Let's try it for n equals 1. I'm lazy. Let's try it for an easy one. Well, if n equals 1, this would say 1 squared, and I stop, is 1 times 1 plus 1 times 2 times 1 plus 1 all over 6, which is 1 times 2 times 3 over 6, which is 6 over 6, which is 1. That's what we were supposed to get. This formula, what formula am I talking about? Sum as I goes from 1 to n of I squared does seem to be this. This is not something to memorize, but it's something that we need in our main problem for today. By the way, there's similar formulas for the sum as I goes from 1 to n of I, and sum as I goes from 1 to n of I cubed, etc. Sum as I go from 1 to n of I to the 4th. They're similar formulas. You could look those up, Google them.